Yes, hello. I'm Andronikos Loukidis. I'm a PhD student from the University of Stavrakas, Department of Electrical and Electronic Engineering. And I will present you our work entitled Electrical Methods for Assessing Damages in sand mortar beams combined with acoustic emissions. Our aim is to monitor the damage level within mechanically loaded specimens made of cement mortar materials in terms of the change of their electrical resistance. In total, I will present you two beam-shaped specimens, which were subjected to three-point bending at deep fracture, and where we had concurrent measurements with electrical resistance and acoustic emissions. We will also investigate the possible correlation between the change of the electrical resistance and the acoustic activity expressed in terms of the F function. And furthermore, we will try to detect the entrance in criticality for the existence of power loss during the last stages of the loading protocols. Both techniques have some advantages, especially the electrical resistance. The variability of the electrical resistance could be attributed to mechanical, microscopic, and reversible effects. It is through the electrical resistance we can monitor the damage infliction and the subsequent microcrack opening, and also the healing process due to the microcrack closing. The first one, through the first one, we can see an increase in electrical resistance, while in the second one, we can see a decrease of the electrical resistance. For acoustic emissions, it's a widely used on surface technique, which originates from the earthquake observation, and they refer to the transient elastic waves, which are generated by the energy burst when structural changes occur in the bulk of material. In total, as I said, we examined two specimens. Their dimensions were 50 millimeters to 50 millimeters to 200 millimeters. The ratio used for the molding was 1 to 3 to 5 cement, sand, and water. The sand grade diameter was approximately 3 millimeters, and both specimens were cured for 2 days at 20 degrees and 100% relative humidity. We tested them after 90 days in order for them to obtain 95% of the total strength, and the loading and quasi-static loading conditions were adopted under load control mode and a constant rate of 20 newtons per second. For monitoring the electrical resistance, two cold plate electrodes were implemented during the casting of the specimen, and their location were near the center of the specimen where the crack initiation and propagation was expected. Here we can see our experimental setup. For the acoustic emission detection, we used a Mistras Group PSI-2 system. And for the electrical resistance, we used a high resistance meter, a Keithley 6517. We will monitor apart from the F action, we will monitor the changes in the acoustic emission altitudes through the improved B value. And I will now talk about a little bit for the F action. The F action is actually it represents the average frequency of occurrence of acoustic emission hits or events. In our case, we will use the acoustic emission hits. Each value of the F action is reflected to an average time, which will be symbolized with a Greek T, as you can see over there. Here are the results for the first experiment. Figure A shows the temporal evolution of the electrical resistance in juxtaposition with the load applied. The second one depicts the same thing, the temporal evolution of the electrical resistance versus the applied load, but in a different scale, in time to failure parameter, where TF is the time where the fracture of the specimen was occurred, and the horizontal axis is logarithmic. The time to failure parameter is provides better clarity on what happens during the last seconds before the occurrence of the catastrophic fracture. Notice here that a power law emerges from the 23rd second before the fracture. You can see it here with the yellow box. The figure C depicts the time evolution of the B value, again in a time to failure scale, and the D figure also depicts the evolution of the F action in a time to failure scale. Here we also see a power law that emerges after the 24th second before the fracture of the specimen. The same thing here for the second specimen. The first one is in a time scale. The first figure is a time scale where the electrical resistance is plotted against the load applied. The second is the electrical resistance versus the load, but in a time to failure parameter, in order for us to see if a power law appears. The third figure also shows the time evolution of the B value. Notice that a sudden decrease of the B value is observed. And the fourth figure D, depicts the evolution of the F action versus the applied load for a time to failure parameter, where again we see the existence of a power law. Here I show you for both specimens when the existence of a power law is depicted, is observed. Again, in a time to failure parameter. In conclusion, what I've shown you so far is that for both cases of specimens, a power law in the case of electrical resistance, a power law appears when the load exceeds 90%. A similar behavior is also observed for the F action. The existence of a power law, and that these findings are in full accordance with those from other experimental protocols, especially in cement-based materials and marble. Notice that the exponent is not the same for both both specimens, and additional experiments should be conducted before definite conclusions are drawn. And thank you for your attention.